Hello, everyone. Welcome to Construct Innovate Webinar Series on digital construction technologies. You're very welcome. My name is Magda Hajdukiewicz. I'm co-director of Construct Innovate, Ireland's National Research Centre for Construction Technology and Innovation. And today's webinar is on simulation for better performance. And we have three wonderful speakers with us today. The first one is Dr. Rubina Ramponi from Arup, who will be speaking about numerical simulations of the indoor and outdoor environment. Our second presentation is from Dr. Yadong Yang from University of Galway, who will be presenting on wind turbine simulation and its application for performance optimization. And our final presentation today is from Dr. James O'Donnell from University College Dublin on data integration methods to support national scale residential renovation. We're going to start with the three presentations, and this will continue with the Q&A session at the end. So if you have any questions to our speakers during the presentations, you can write those questions in the Q&A box at the bottom of the screen. So without further ado, I'm going to ask Rubina to share her slides, and for everyone, enjoy the presentations. Thanks, Rubina.
Thank you, Magna. I'm just gonna share my slide. Hopefully you can see it.
Yes, perfect.
Yes. Good afternoon, everyone. And yeah, thanks for joining this webinar today. My name is Rubina, and I'm a senior engineer at Arup in our Dublin office. I'm very excited to opening this session on simulations for better performance. And I wanted to talk to you about numerical simulations and how we can use this tool for improving the design of indoor and outdoor environment. So in the next 10 to 12 minutes, I just want to give you a brief information about myself, and then sort of like understanding what is the value of numerical simulations for design and a few examples of situations where numerical simulations have been useful to respond to design questions. So this is just about who I am. So as I said, I work at Arup and I'm a senior engineer, and my specialty is wind and microclimate. I actually have a design background in building engineering and architecture, but I came across numerical simulations at first during my PhD, where I analyzed the ventilation potential of buildings that are placed in the urban environment. So I've combined some fluid dynamic simulations with energy simulations to understand the potential for natural ventilations. And after my PhD, I joined Arup about 10 years ago, actually this week. And I work in the UK, in the US, and in Ireland, doing both experimental and numerical modeling of wind, climate, and microclimate. So I gained quite of an appreciation of the cases where numerical simulations are useful and what they can add to the design. And that's really what I wanted to share in this presentation today. So before starting with any of the technical details, I wanted to kind of like reflect on when do we use numerical simulations and why they're useful. So if we look at this picture, this is an atrium of an office building in San Francisco. And I think you can immediately see that people use this space in many different ways. And this space is complex in terms of functions and what people do, but also in how these interact with the outdoor environment. So you can see the person on the bottom right is working on this co-working area. Then there is a space on the stairs with some informal meetings and chats. And then you can't see it very well, but at the bottom left is a cafe that is open to the public. And then there is a person entering on the bottom right because the space is fully open to the outdoors. And when we design this space, one of the first questions is that how often can be used, or is that comfortable for people and for how much of the year? And this is not a very easy answer, easy question to answer, because we would need to know the environmental conditions in every single point of this space to be able to quantify comfort and also to understand for how long these spaces are comfortable for people. And so this is a good case, I think, of when do we use numerical simulations in the built environment. And I'm going to focus mostly on comfort and sort of like a user experience of those spaces. There is a large variety of other sort of like cases for this type of tools. So broadly speaking, I think we are interested in using numerical simulations when we want to account for variable climate conditions, when guidance from code or simplified tools are not enough really to respond to design questions, and when we need to provide a a granular picture of how the environmental conditions vary in a space that is either an indoor space, an outdoor space, or a space like this where it's very important the connection between the indoor and the outdoor environment. And often in design projects, we need to face unique problems. And so numerical simulations have the flexibility to tailor to different project questions. So if we think about the user experience of the built environment, there is several factors that affect the person perception and comfort in the built environment. So from our environmental side and personal side as well. But broadly speaking, I think we can think about three main sort of like areas. So normally we account for the local climate and how this is influenced by the built environment and by the proposed development specifically. So how all these interactions in the built environment work and change the climate. And then we would need to sort of like calculate and address some performance targets. And this is really when numerical simulations come to rescue, because they can model this interaction between the climate and the built environment and help us obtain or check performances. And then if these performance targets are not met, then we can test different options and different climate conditions as well. When we think about numerical simulations, there are very different type of numerical simulations on the environmental side that we can carry out. So these are just some of them. And I think many of you probably immediately thought about energy simulations, but there is also acoustics, air quality, daylight, sunlight, and wind and airflow. And these last one are really what I wanted to focus on today, because we do carry out quite a lot of simulations in our work, but I feel this is a topic in the industry that is yet to be fully explored and understood. So when we think about wind and airflow simulations, normally we talk about CFD tools, so computational fluid dynamics tool. And in a nutshell, I think the CFD first creates a virtual model of the proposed development. The picture that you see here is from an academic paper from Professor Bert Blocken. And you can see that the computational domain really is able to reproduce the built environment in quite of a high level of detail. So we first create a computational model, and then we can use it to test different options and climate conditions. The video on the right is the design of a stadium where we needed to model both the external environment, the internal environment, and what happened on the sort of like envelope. So in this cavity between the two layers of the roof. And you can see that the CFD could really reproduce the flow and get us an understanding of the flow in all these three parts of the domain. And CFD also helped us to model different climate conditions and different design options so that we could help optimize the design. So when I was trying to think about the added value of running numerical simulations for the built environment, I think really what we aim at the very end is to have an integrated approach where we can understand the impact of a specific building with their surroundings and how that sort of like relate with the climate and with the different specialties as well. So I pointed out 4 areas that I thought were interesting, but there's not the only one of the advantages of running numerical simulations for the built environment. So first, I think a numerical model really help us understanding the interaction between different systems or the effects of surrounding buildings and different elements of the built environment. We do test several climate conditions, so simulations can account for current or future climate scenarios and understand the climate impact. Simulations can be carried out at different stages of design, so they really help with the decision making at different design stages. And we know that as much as we can like offset decisions on the early stages of the design is where we can really gain the best advantage on reducing the cost and really influence the design down the line. And then simulations can help us, the results of numerical simulations can be integrated with each other to sort of like build a better picture of what are the environmental processes going on in the built environment. So for instance, we can combine the results from wind models with solar results and historical data of climate to get an understanding of thermal comfort. This is just one of the many examples that we can find to see how these processes are combined. So I wanted to just go through 4 different situations where having numerical simulations have really helped to respond to the design questions that otherwise wouldn't have been very easily solved with simpler methods. And so I'm just gonna go through those briefly. The first is wind microclimate project. This is a pretty typical questions in Ireland because buildings that are taller than their surroundings or taller than about 6 stories tend to sort of like bring stronger wind down to the ground, and sometimes they create wind issues as like for pedestrians and cyclists. And so they are often required to be addressed as part of the planning process. And this is very frequently done with numerical simulations. And the advantage of using numerical simulations is that we can, as opposite to, say, for example, understanding how the wind works in a building in isolation, we can really account for the effect of the surrounding buildings, the different wind directions and speeds, and also the effect of landscaping and hard landscaping elements that have been designed. Or we can support the design in sort of like try to find mitigations and elements that can be integrated into the design itself, but also be helpful to reduce windiness in sensitive areas around the development. This is a study of re-entrainment. So it's a academic lab where some pollution was exhausted from the roof, and there was a risk of some pollutants to enter the ventilation system that was placed on the other side of the building. So this is a pretty typical case for industrial facilities like data centers or pharmaceutical or academic or industrial labs. And the way we would normally resolve these problems is that we analyze the mechanical systems and then the climate conditions and try to understand what are the climate conditions that are more critical for the design. And then we can carry out numerical simulations of the building itself. So as you can see, we can reproduce pretty well both the massing of the building and also the locations and characteristics of this exhaust and intake. And then we can use those simulations to help understand the risk of this entrainment to happen. And then we can work with the design team to try to reduce those risks and find design options that can mitigate the risk itself. I thought this application is interesting because it's a very different scale. So we can use simulations not only for larger spaces, but also for detailed modeling of smaller scale problems like a double skin facade. So this was a double glazed panel unit where that was ventilated from some slots on the sort of like intake at the bottom of the panel and then exhaust on the top. And there was a question regarding the temperatures that the air inside the glasses could achieve and see if we could compromise the performance of the glazing units. And so with traditional methods or thermal analysis, we could get a very simplistic view of the results, but CFD really helped us understanding the stratification inside the glass and also the air distribution and the velocity across the whole panel to visualize and understand the sort of like air processes inside the cavity. Finally, this is a case of indoor ventilation for a classroom. During COVID especially, there was a lot of concern of how the airflow would distribute inside indoor spaces and what was the best mechanical strategy to provide a uniform ventilation across the space. So CFD was used at the very early design stages to test the effect of different ventilation systems on the airflow distribution inside the classroom. So you can see on the two figures of the bottom that CFD also help kind of like visualizing that flow and see if all the corners of the classrooms have actually access to the air distribution. So hopefully this, for example, gave you an idea of how CFD can help us understand how our building interacts with the buildings around it, and also how the single system can interact with each other, and how can we model those interactions and visualize them and estimate them using numerical models. You have seen that in all these cases, there was an interesting and important contribution of the climate characteristics that we could reproduce with CFD. So normally we use numerical modeling, but it's coupled with an analysis of historical data of the climate so that we can understand what are the most important conditions to simulate. Those simulations can be used at different stages of design. And some of those examples were from an early design stage where we needed to take decision early on, and some others were more focused on a detailed design where we needed a more specific answer to a configuration so that we can then go back to the design and revisit the strategy. And finally, simulations can give you a good picture of the processes driving the environmental flows, so especially when we combine them, and we can extract different metrics that would not be possible to calculate with just one discipline alone. So just to wrap up, I just wanted to close this presentation with a bit of a broader question. So numerical simulations are available and used for the built environment. My impression is that we are not yet really leveraging on their potential to influence the design at all stages. And so I think there is a broader question on all sides of how can this complex tool be more integrated into the industry, if it's either being made more accessible or more understood, so that we can fully integrate those tools in all stages of design and really make the most of their potential. Thank you very much.
Thanks very much, Rubina. It's a great overview of computational fluid dynamics and some case studies there. Fantastic. I'm going to ask Yadong now to share his slides. Yadong, whenever you're ready.
Yeah, sure.
Thanks.
Okay, can you see my screen?
Yes, we can.
Okay, perfect. Yeah. So, hello everyone. My name is Yadong Jiang, and I'm a postdoc researcher working at the University of Galway. And thank you for inviting me for this webinar series. And today I will present the wind turbine simulation and its application for performance optimization. And here are the contents of my presentation. So after a short introduction to the group and to the wind energy in Ireland, I will go through the method of analyzing wind turbines and a case study focusing on optimization of the performance of a wind turbine using this methodology, and with conclusions. So first of all, I'm from the Sustainable and Resilience Research Group, and which is founded and led by Professor Jimmy Coggins. And the group focuses on many different areas like the design and the testing of large-scale composite structures, and like the wind turbine, tidal turbine blades, aerospace components and foams. And besides that, the group is also working on the sustainable process and the resilient buildings. So now move on to the wind energy. So as a country with great wind source, Ireland has a good potential to utilize the wind energy. The first commercial wind farm in Ireland started as early as 1990, and up to 2022 last year, there are over 300 wind farms in Ireland, which contribute to 36% of the total energy demand in Ireland. And this 36% makes the Ireland rank second in the worldwide in producing wind energy, just after Denmark. So for months with good winds, like say February last year, wind energy can supply as much as 53% of the national energy demand. So to capture wind energy, we need wind turbines. And besides on the water access, there are two kinds of wind turbines. The first one is a horizontal wind turbine. Its rotating axis is horizontal, and it can have 2, 3, or even more blades. And if the turbine has a rotating axis in vertical direction, it's called vertical axis wind turbine. And in this presentation, I will focus on the most commonly seen wind turbine in our daily life, which is a 3-blade horizontal axis wind turbines. So how does a wind turbine work? So we know that if there is a wind blowing, then the rotor starts to rotate. But what's the theory behind that? So the theory is that the blade is a blade of the wind turbine, and the blade is a key component which directly interact with the wind to capture wind energy. So the wind energy can be converted to electricity through kinetic rotation. And the blade is designed with an aerodynamic shape. So let's take a look at the cross-section of a blade. And the cross-section is an aerofoil, which is similar to the wing of the aircraft. And the airflow is split by the foil, and the benefits from the aerodynamic shape. The flow speed on the lower side will be lower on the flow speed on the upper side. And according to the famous Bernoulli's principle, so lower fluid speed will cause high pressure, and high speed will cause low pressure. And these differences in the upper and the lower side will generate lift force and drag force to the airfoil. And as you know that the blade is constructed with a series of airfoil, so the wind will generate a series of lift and drag force along the blade. And to analyze these lift and drag forces, these two equations can be used. And you can see that these forces are related to the air density, the flow speeds, the section size, and the lift and drag coefficients. So if you can see that if you increase the flow speed, like the wind speed, or if you increase the lift and drag coefficients, and you can get more force, that means more energy can be generated. And the lift and drag coefficients are related to the foil shape and the angle of attack. And this angle of attack is controlled by the pitching system of a wind turbine, and it's quite important. And why? Let's take a look at the plots. This plot shows the relationship between the lift and drag coefficients and the attack angle of the airfoil. So you can see for different angle of attack, you can have a different lift and drag coefficients. So that means you can control the angle of this blade so that you can increase the lift and drag coefficients, and you can capture more energy, makes the wind turbine more efficient. And sometimes when the wind speed is too high, then you can reduce the angle of attack. Then you can reduce the lift and drag coefficients. So you avoid the overloading of the wind turbine and protect this blade. So after you get the forces on the wind turbine, then these forces will generate torque to the rotor, and the torque will make the rotor rotate, and this rotor is connected to the generator, so that this generator can convert kinetic rotational energy to electricity. And of course, besides the torque generated around the hoop, you can there are other forces in other directions, like the thrust, yaw torque, and so on, that forces are all acting on the hoop of the rotor. And together with the wind loads that acting on the tower, all the forces will be transferred to the foundation. So you can see that the forces on wind turbines are quite complex because it's fluid and it's dynamic. So it's fluid dynamics and it's quite complex. And since the forces on a turbine are very complex, we usually use software to analyze the forces on the turbine. And the first very commonly used method is the blade element momentum theory, which is a fast and basic approach performed in two-dimensional space. And you can use many softwares like the OpenFast, Hawk, Bladed to analyze the forces on wind turbine using this BEM theory. And besides that, you also have the computation of fluid dynamics of CFD analyze to analyze the forces on the turbine. And it is a very detailed three-dimensional analysis compared to the blade element momentum theory. And of course, it's very computationally expensive, but it's more accurate. And you can, if you want to perform a CFD analysis, you can use the software Against Fluent, Box CFD, and OpenFOAM. So in the next few slides, I have a case study that is using the blade element momentum theory to perform the analysis and the optimization, which is the simplest, I think, simplest way of analyze the wind turbine. Yeah, so the case study is part of the project, which is called Reblade, titled like as a reblading of Irish wind turbines using novel techniques. So first, just a little bit background about this project and why we are doing this case study. That is because wind turbine is not like other type of buildings, mainly because its design life is 20 to 25 years. So the design life is quite much shorter than other buildings. So that means back to the early 2020s, the wind turbines installed in that time will reach their end of life shortly. And to extend their life, one option is to replace the old blades with a newly designed one to make this turbine continue to generate energy and extend their life. So this project is proposed with two partners, Air Composites and the ESB, and the main objective is develop advanced technology to retrofit aging turbines through reblading the turbine with highly efficient and resilient blades. So this case study is just to try to optimize to design a new blade that will make the turbine have a better performance. And when I mean performance, I mean the power production rate. So the wind turbine we focused in this case study is Vestas V27 wind turbine, which is a small wind turbine with 225 kilowatts power capacity. And the blade is constructed with a modified LAC 6 series airfoil, and it's 30-meter long, manufactured by Air Composites using the glass fiber reinforced composite materials. So to simulate the operation of the turbine and get the forces and torque, I used the blade element momentum theory that I mentioned in the previous slide. So after doing simulation, and I get a power curve of the V27 wind turbine. And here I plot the power curve from the numerical simulation based on the blade element momentum theory with real recorded tested data from the real operation. So you can see that although the blade element momentum theory is a very simplified two-dimensional method, it can capture the power curve of the wind turbine wheel. So this validates this method, so we can continue to do some optimization works based on this BEM theory. So to optimize the performance, they need to increase power production. The objective is try to change the external shape of the blade, like the foil shape, size, and twist angle, to make the blade capture more energy. And to do that, I used the genetic algorithm, which is commonly used algorithm to do some optimization works. So here is a flowchart to which summarize the genetic algorithm. So initially, it generates a set of inputs variables here randomly, and when I mean the variables means the foil shape, the size, and twist, and this will define the blade's external geometry, and that is the input parameter here. And then when you have the input parameters of the blade, then you can generate the turbine model based on the BEM theory. And this theory was validated by testing data. So we have confidence on that. Then based on this analysis and simulation, we can get the power curve. And based on this power curve, I can make a judgment on if it's good or it's bad. Then we will try to repeating the common procedures of a genetic algorithm, like the selection, mutation, crossover, and elimination, to keep generating different blade geometry and keep analyzing different turbine performance. And based on the results, we can select the one with the best power production. And in this case study, actually, we did 4 case studies here. So the first one, we just optimized the chord width of the blade. For the second one, we optimized the twist angle of the blade. For the third one, we optimized both the chord width and twist angle. And for the last one, we consider every parameters. So here are the results. So these plots shows the plots on the left lower side shows the comparison of the power curve of the 4 blades together with the reference blades. So you can see that the power production of the blades is more sensitive to the chord width and to the airfoil thickness, and is less sensitive in twist angle. And second observation we know that is when the wind speed is higher, I say rather than larger than 10 meters per second, then it will have a good improvement in the power production. While for the no wind speeds, there is less improvement. So that's a result just get from the power curve. But we know that for different locations, you have different wind distribution. Then that means you may have different performance of these blades. And here we selected 12 different locations to perform simulation to get the annual power production of different turbines. And we found that on average, the blade 4 will have the highest improvement with an average of 4.2%. So that blade 4 will be the final blade that we adopted. And here is a geometry of the optimized blade, which is blade 4. And you can see there is a lot of change in the twist angle, in the chord width, and in the foil thickness. And in the future, this optimized blade will be manufactured and will be tested for further validation of this methodology. So here are the conclusions of my presentation. So we go through the methodology to analyze the performance of the blades. based on data elements from the series, and combine this series with genetic algorithm. We can do some power production efficiency optimization of the plate, and we get good results with an average improvement of 4.2%. And that is a case study to validate the proposed methodology. And here I'd like to thanks for the support from the SEAI, from SFI, and from Marine Institute. And thank you for your attention.
Thank you very much, Yedong. It's a great example of using digital tools to optimize the wind turbine design. I'm going to ask James now to share his slides for the final presentation. James, whenever you're ready.
Yes, hello everybody. Good afternoon. Okay, shall we just start from there? You can all hear me okay?
Yeah, we can't see your slides yet.
You can't see the slides yet. Okay, so I need to share screen. Like that?
Yeah, that's perfect. Thanks.
Super, I'm just moving my Zoom toolbar out of the way. Okay, great. Super. Good afternoon, everybody. And I'm James O'Donnell from University College Dublin. My group formed the Building Energy Informatics Lab, and my presentation today will look at data integration methods to support national scale energy modeling. So this is multi-domain, multi-scale energy modeling. A lot of work involved and a lot of data that needs to be collated, structured, and processed in order to support that type of modeling. A lot of help from my colleagues, senior researchers, Dr. Rosemary Ali and Cathal Hoare. Okay, next slide. So I have 4 key parts of the presentation, and we'll get straight into it. So I think a lot of the people on this call will be familiar with the Irish Climate Action Plan 2023. We've set out some ambitious goals regarding renovation targets and also the installation of heat pumps. We see the numbers here in front of us, and they're quite enormous values given the rate of heat pump installation and rate of renovation we have in society today. We also saw yesterday in the news that the renewable energy targets for 2030 were brought into doubt through a survey of private and public workers in the area. So these are ambitious targets and may not be realistic, but let's keep pushing on and see what we can do. I'll return to these numbers in a few minutes. It's not all negative. There have been blueprints and roadmaps that have been successful. For example, in Finland, a country that's comparable to Ireland in population size, they have a significantly higher rate of heat pump adoption, for example, than we have in Ireland. You can see here the comparison on the right-hand side. But they have had a key strategic advantage. Their buildings were simply at a much higher quality in the first place. So their residences have far better U values, far better air tightness, and the heat pumps were installed as a system of systems approach. So you can't just install a heat pump into an existing building unless that building is lower energy to start with. You can, but it'll cost you a fortune to run it. Okay, so an approach we kind of look at in Ireland, if we're looking at kind of top-down energy modelling approaches or stock-level modelling scenarios, would be to consider archetypes. If we see here a breakdown of approximately 2.1 million Irish residences, we see kind of the typical forms we're used to dealing with, from detached to semi-detached, terraced houses, bungalows, duplexes, and even some temporary dwellings. Okay, so as part of our extended work at the Building Energy Informatics Lab, we've developed a series of representative archetype models. So we have, for example, on the screen here, we've 5 different types. I don't need to list them out, just let's pick one, for example, a detached house. So what any given archetype would do is to have properties that are representative of all of the detached houses, for example, in Ireland. And then we can have different variations in terms of occupancy values, of insulation values, of say renewables or not, and so on. So there's no end to the number of different variations we can have on a given archetype. And it's important that we have a systematic approach to storing those different types and the outputs from the energy models that are associated with those different types. So I wanted to highlight the complexity of the decision-making environment when it comes to stock level modeling here. So what we have in this case is a 60-year renovation. We took that detached archetype again, and this was in conjunction with Arup on behalf of the Peter McVerry Trust. So this report is soon to be published, and I just thought I'd show one graph from it. So on the left-hand side, we have two y-axes. It's very, very important that we note the first y-axis here on the left, so it's total carbon emissions per year. On the right-hand side, we have total cumulative carbon emissions. So let's just start at the beginning. For any given renovation project, a detached house, for two scenarios, one in red, one in purple. So in red, we have a detached scenario where we have a condensing gas boiler that's added to the building in conjunction with a range of fabric retrofits. The scenario in purple is a heat pump renovation that has the same fabric retrofits, but instead of the condensing gas boiler, we have a heat pump. So that explains the difference in embodied carbon associated with year one of the renovation. So a heat pump is far more carbon intensive than a boiler, for example. We then have a range of carbon emissions over each year for a 60-year life cycle. And we see here straight away that the carbon emissions associated with the boiler case on a year-by-year basis are higher than the carbon emissions associated with running the heat pump. And key observation here is that it takes maybe 7 or 8 years in terms of a balance point, but this is highly debatable in terms of how we reach that balance point. Going back to those national targets I mentioned on the first context and motivation slide, what we have modeled is for the projected reduction in grid carbon intensity. So we see here a drop off in the purple values from our current levels, quite a sharp drop off as far as 2030. But if that, and that as a result shows that the heat pump is certainly a better renovation case at the moment, if that was to be the case. And we also may note here that the heat pump is set to be replaced every 17 years and the boiler every 15 years. Those values can be played around with, given industry norms for a boiler might be actually 20 years and a heat pump 15 years. So we end up with a far closer alignment of these two lines after a period of about 15 years. So the key point I'm trying to make here is that there's huge uncertainty associated with these decisions, and particularly at a stock level, it's very, very challenging to make the right decision, and making an informed decision requires a lot of information. So I'm going to keep that in mind as we push through the rest of the presentation. So I've developed a research question here, and looking at kind of what type of information do policymakers need if they're going to renovate at a stock level, and then that will help them inform the appropriate pathways to take for a given country. We've also formed a hypothesis here that I don't need to read out, but essentially those policymakers can go ahead and consider the important domains of interest, from health, from indoor environmental quality to energy consumption, carbon emissions, etc., as they make those decisions and formulate the policy based on that information. Okay, so a key project we have that's looking to achieve this and bring this information together and allow for appropriate energy model to be created is in conjunction with partners at the University of Ulster and also Penn State University. So it's funded by Science Foundation Ireland. And we have 3 different distinct components, the first of which UCD is responsible for. So we're responsible for data acquisition, and those data are in heterogeneous form. So, for example, we might deal with census information, BER data, LiDAR scanning, photogrammetry, etc. So there's a whole range of different sources that we need to process. We also need to organize that information and store it and interrogate it. Our colleagues in the US will look at a lot of machine learning based models that pulls information, data information from what we just collected here on the UCD side. And all of this is being informed by our colleagues at the University of Ulster with regards environmentally benign approaches and technical, socio and economic factors that play into the key decisions that need to be made. Okay. So I think it stands to reason there's a lot of information required to analyze a given building, not to mention a building stock. And one key issue is a lot of that information can be significantly large in volume, it can be complex and also siloed. So we're looking at pulling this information together in a form that's readily accessible. So we developed a concept called a common context. So as energy modelers, we've seen earlier, say, a wind turbine context or a CFD context for a stadium. But in the context of what I'm dealing with here, we look at, say, a building or a zone within a building, or that building is part of a neighborhood. These are all geographical contexts that are of interest to energy modelers. So we developed this generic context object that can be instantiated at different levels. So what do I mean by that? So, for example, we were faced with a challenge by the ESRI. They said that if all of those heat pumps, 600,000 heat pumps, were actually implemented in Ireland for Irish residences, how would the transmission grid be affected? And that's a very challenging question to answer. So we developed the appropriate geographical context, and I'll show some more detail on the next slide. We developed a tool that allows us to define those contexts, instantiate them, link our transmission grid to our small areas, which we're all familiar with, or our small areas or neighborhood level, and then appropriately link with the building instances. And it is very important that once those links are established, we can then pull in information that are related to all of those individual contexts, link it together and query the entire data set. So it's very, very important. We see here it's a more detailed representation of the geographical context we're dealing with. We see here concepts and contexts we're familiar with: a county, a town, an urban area, a thoroughfare or street, the building itself, and then the building as an address and an air code and so on. We also have the small area over here on the right, and we can pull in some images or BER certificates as an example. So there's a lot of complex information and heterogeneous information being brought together for that. Okay, so a little more detail on how we've done that. So we see here we have the transmission system represented geographically up here in the top right. We also have all of our small areas. Then for each small area, we have a number of different archetypes, and the energy profiles associated with the archetype energy models are fed into those archetypes. So that full data set is then queried, and then we relate the projected increase in electrical energy consumption back to the transmission nodes and evaluate for overtime and at peak times. So there's quite a challenging exercise in terms of data acquisition and processing for that particular exercise. Okay, so I'm just showing here that the overall vision then, as we move on from that particular example, the overall vision or overarching vision for this work is to be able to really extend it and scale it up and make it available for multiple national building stocks, not just Ireland. So I just want to show an example of the types of data and information that we can deal with. So I mentioned the European Energy Performance Certificates, or BER ratings, as we're familiar with them. Geodirectory, also very, very useful, a lot of very valuable information in there. We also have some upcoming work to be published on extracting U values for walls and windows based on photographs and some geographical context information. We know, based on significant previous work, that there's 16 to 18 key parameters that we really need to know about any given building. And if we have that information accurately available to us, we can make a pretty accurate determination of the state of the building and the energy consumption of that building. Census information helps enormously. We all know the importance of occupants with regard to energy consumption. And we also have then a whole range of different energy modeling techniques, be they white box models such as Energy Plus or IES, or machine learning models, or even grey box models, which are a combination of the physics and the data-driven approaches. Okay. Also see significant approach for scaling, significant potential for scaling this approach to include the other utility networks, down to, for example, the distribution nodes. Maybe consider energy flexibility of buildings, embodied carbon databases, district heating opportunities, and many, many more. Okay, so I'm just going to show a few results then from our energy modeling side of things, to building upon this large data set that's ever increasing. So we took, for example, a series of buildings for Dublin. We didn't have all of the data we needed, so we generated a synthetic data set, so energy models for about 1 million Irish residences, using the 4 different archetypes we see below. We then ran them through a whole series of an ensemble of machine learning algorithms, and we can see here that our ensemble segregation approach at the bottom was returning the best results with an accuracy of 91% and the lowest root mean square error. And so on. We also see an R-squared value of 1, which is very, very high for this approach. Okay, and the more information available on that paper at the bottom of the slide. Okay, so I mentioned, policymakers and so on. Like a lot of the machine learning algorithms and so on are not typically used by policymakers. So we've developed dashboards and so on to make this enormous data set available to those policymakers, where they can actually, through a series of slider bars and drop-down menus, select appropriate values for given parameters, and that the corresponding energy results will update accordingly in such a database. So this is very powerful, given the fact that it's pulling from such a large database of information. Also, another format we've used so to plot our results in GIS and accordingly, and particularly here at the bottom of the screen, we see if we pull together all the energy, population, retrofit grant, and socioeconomic factors, we can very easily highlight the small areas or neighborhoods that should be prioritized in terms of renovation. So those types of neighborhoods will give the best value for Ireland or a given country in terms of where to start the renovation and then where to continue. Okay. So in conclusions and future work then, huge opportunities. A lot of this requires high quality data, and there can be significant work associated with actually pre-processing the data to remove outliers and inconsistencies and so on, and ensure that we have a set we're happy to work with. We really need the stakeholders, particularly the policymakers and so on, to be comfortable with the interfaces that they're operating with and to be confident in the data that they use. Okay, and again, I think our next step is to start working in a more serious way with embodied carbon information, as I think life cycle approaches and not just the operational phase of the life cycle are most important. So I'm going to wrap up with that, and I'd love to take any questions.